Alongside Colin Maclaurin we had Brooke Taylor, and Brooke Taylor also did some work on power series. And his work was to say that what Maclaurin did could be expressed in the following form. So really this would be f of x plus 0, where he then noted down that the 0 that was used here was used throughout our equation. So he looked into what would happen if we looked not in a location near 0, but what if we looked in a location near some unknown point a. And what we would end up with here is f of a, x lots of f prime of a, x squared over 2 factorial f double prime of a, and so on. This was one of the things that he looked into. Something else that he looked into was a slight transformation here. So if we take, instead of x, we let that be x minus a, then wherever I've got an x, I'm just going to replace that with x minus a. So in here, and so on all the way down. And that then gave us the following. F of, well, x minus a plus a gives me f of x being equal to f of a plus x minus a f prime of a plus x minus a squared all over 2 factorial f double prime of a, and so on. And these were two power series expansions that we can use that give us an approximation to a function in the location or the locality of a point A. Obviously we don't need to remember them, they are here in the formula booklet, so let's now just go along and have a look at how they can be used. So in this question we're asked to find the Taylor expansion of e to the x in powers of x plus 3, up to and including the term x plus 3 cubed. Now if I go back to my power series, if I'm wanting something involving x plus 3 in powers of x plus 3, not in powers of x, I'm looking for things in powers of x plus 3. That's more akin to the top formula. So this is how we decide which formula we are going to use for a Taylor series expansion. So that's why at the bottom of my page here I have the x minus a expansion. Now our x minus a is in fact x plus 3. This tells us that the value of a that we are using is negative 3. Now in a similar way to our Maclaurin series, the first thing I'm going to do is just to write down my functions and their derivatives. So f of x is e to the x, f prime of x is minus e to the minus x. Just quickly filling out the other differentials. Obviously I stop at f derived 3 times because I'm only looking for up to the term cubed. Okay, so our next job is then to substitute in our values because we want to find f of a, f prime of a, f double prime of a. So then we just substitute in. So moving across we have f of minus 3 is e to the power of 3, and again just quickly filling in the rest. Okay, so now I'm at this stage, it is just a case of substituting into my formula. So I know that my f of x function, which is e to the minus x, can be approximated by f of a, which I've now got down as e to the power of 3, plus x minus a, well my x minus a was x plus 3, lots of f prime of a, which is minus e to the 3, plus x plus 3, sorry, all squared over 2 factorial, f double prime, which was e to the power of 3, and my final term okay, and I'm just going to choose to pull out a common power of e to the power of 3, and then this becomes 1 minus, so let's get rid of that, 1 minus x plus 3 plus x plus 3 squared minus x plus 3 cubed. In our next example, we're asked to express tan of x plus pi by 4 as a series expansion in ascending powers of x, again up to and including the term in x cubed. So again, if I hop back to my formula booklet, we can clearly see that what's given to us in ascending powers of x is the second expansion, where I've got x, then x squared, and x to the power of r, and so on. So that's what I've got set out on the bottom of this page, is my formula set up this way. Okay, so as per usual, what I'm interested in is evaluating the derivatives of my function. So my function in this case is going to be tan of x plus pi by 4. So my f of x function is, let's just say, tan x. Now f prime of x differentiate this using the chain rule, so bring the power down. Sec differentiates to give me sec x tan x, and then the original function. This we can get from the formula booklet, and then we can just tidy this up. Now for our complicated derivative, similar to before, chain rule, this becomes 4 sec x tan x, by differentiating now inside the function, the sec x. Now the larger function itself, the 2 comes down, and this leaves me with sec of x multiplied by tan of x. So now I've differentiated my first function. Product rule, I now need to differentiate my second function, so leave the first one alone. This becomes sec squared, tan differentiates to give me sec squared x. Okay, just quickly collecting some like terms here. I've got 4 sec squared x tan squared x plus 2 sec 4x. My next step, of course, is to evaluate these derivatives and functions. So the first one will be f of pi by 4, which gives me 1. F prime of pi by 4 gives me, well, sec squared I know is 1 over cosine squared x, so this will be cosine evaluated at pi by 4. Cosine evaluated at pi by 4 is 1 over root 2, so I end up with 1 over root 2 squared as my denominator, and sorting all of that out, I end up with 2 f double prime of x of pi by 4. Well, sec squared from my previous one was 2, tan is 1, so I got 2 times 2, which is 4, times 1 gives me 4. And finally, the third derivative, evaluated at pi by 4, is going to give me 4 times 2 times 1 squared plus 2 times, now this is sec squared squared. Sec squared I know is 2. 2 squared gives me 4, so this is also 8, and 8 plus 8 gives me my final answer, which is 16. So just remembering that this is 4, 2, and 1, plus 2 times 2 squared, gives us our final answer. At this point I can now go straight to my formula, and I can write in that tan of x plus pi by 4 is equal to f of a, which was 1, plus x lots of f prime of a, which was 2, plus x squared over 2 factorial lots of f double prime of a, which was 4, plus x cubed over 3 factorial lots of 16. And again, I might wish to tidy this up somewhat, because I know I can make this look like 1 plus 2x plus, the 2's will cancel here and give me 2x squared, and again I can get 2's to cancel here to give me 8/3 of x cubed. Thanks for watching. The next video in this series is on solving differential equations using Taylor series.